So, hello everyone again and welcome to my channel. If you remember on our previous video, we talked about how the relationship between the voltage of a particular charged particle and the magnetic field that particular charged molecule is subjected to will generate a force. We looked at the right hand rule and we looked at the cross products, and now we're going to see how we can apply that to a charged particle moving at a particular circular path. Now, let's just look at some terminologies to actually take into account before going really deep into this concept. Now, if we have a particular symbol that is represented as this symbol says that a particular quantity, like for example, I would say a magnetic field, is actually pointing into this particular book. On the other side, if we have a symbol that is actually showing a circular path with a dot inside, then we say that this particular magnetic field is pointing up, which is away towards you, relative to this particular book over here. Now let's go now into this concept of circular movement of a charged particle in a magnetic field. Now, if a magnetic field is pointing away from me, which is in this particular case over there, then we have a circular path which goes like this, and this circular path is actually counterclockwise, and this path is being generated by a charged particle. Could be represented as Q plus or Q minus, which is positive or negative charge respectively. We'll talk about that in later movement. Now, for the case of this particular movement, we consider our charge to be positive charge. So if you have a positive charge, you have a counterclockwise motion in this case. However, on the other side, if we have a negative charge, we will have a clockwise movement of our charged particle. Now, if your voltage is actually pointing in this direction, which is actually tangent to this particular curve over here, what we realize is that when the magnetic field is actually pointing into this particular book, I'll just draw it as an X over here, which is our magnetic field. Our force in every single path of this circle is actually pointing towards the center of this particular circular part over here. Now the circle here, you need to take into account the radius, which is represented as big R over here, and this motion we usually call it a centripetal movement over here. In this case, if you're focusing on the force will be called the centripetal force. Now let's look at the centripetal force. We know that in this case, our magnetic field, which is actually 90 degrees with the voltage, is actually having a sine 90, which is equal to 1. Now, if you plug this into your regular formula, where you have the force equal to the quantity of charge multiplied by, or I'll say the quantity of charge with it, which is actually an absolute value. Then we multiply this by the cross product of our voltage and our magnetic field. What we get is this, which is equal to VB sine 90 degrees. Now sine 90 degree equals to 1. What we get in this case is our force to be equal to the quantity of charge multiplied by the voltage and the magnetic field. Now, one thing you need to take into account is that for the centripetal force, we do note that the force, which is the centripetal force, is actually perpendicular always to the voltage. And now if you know that the quantity of charge is greater than 0, then we consider the movement to be counterclockwise. On the other hand, if you have a quantity of charge to be less than 0, then we have a clockwise motion of our charged particle. Now take note that in terms of our radius, the radius is actually determined by the mass of that particular charged particle multiplied by its velocity, which is a centripetal, I would say, velocity in this case, all divided by the quantity of that particular charge multiplied by the magnetic field. Now this actually gives you the radius of the circular orbit. And then going ahead, if you remember in regular high school, you looked at the average, the angular velocity, and we do know that in the angular velocity, which is represented as this is actually dependent on the velocity divided by the radius of this particular circular path. However, in this particular case, when you're looking at the magnetic field relative to the voltage and how this is actually subjected to a particular charge molecule, this particular angular velocity, which is now called the cyclotron angular velocity, is not dependent on the velocity. However, it is dependent on the quantity of charge multiplied by the magnetic field, all divided by the mass of that particular object. So you just need to take note of this. Really a key concept you need to know. And since you're going to look at the cyclotronic angular velocity, then if you're trying to apply this to our period in this case is actually equal to 2 pi m over qb, which is the charge of the particle and the magnetic field. This actually comes from our understanding of the frequency, which is actually a cyclotronic frequency or cyclotron frequency, which is represented as one over the period, and then we put the period into this particular equation over here. What we get is our quantity of charge multiplied by the magnetic field divided by 2 pi multiplied by the mass of the particular object over there. Now that's about it for this particular video. Take note that the cyclotronic velocity or cyclotronic angular velocity and the period doesn't depend on the velocity, and to some extent the radius, as we see over here, and over here. So that's about it for this video. I hope you're able to understand this. Hit the comment down below, let me hear your thoughts. Peace and be smart. Bye.